the correlation can be important, can give you an idea at the beginning at what variables might influence the other variables. However, important confusion happen with the correlation. You need to be careful when you compute the correlation. For example, if you computed the correlation, let me give you a simple example here. For example, if we have the area and the size of the house or the price, and we find the correlation, positive correlation, (0.7 or 0.6. What does that mean? So the correlation usually is a scale between -1 and 1. If the correlation or absolute value of the correlation between 0 and 0.4, you have weak correlation. 0.5, 0.6, strong correlation. More than 0.6, 0.7 is strong correlation. So here means generally when the area increases, the price is going to increase. The positive correlation. Okay. So usually when we have a data set, one of the explanatory analysis that we conduct, we compute the linear correlation and see is there any dependency. If you have a correlation 0.4 or more, can be medium correlation. Here we might look into more details about this variable, right? So which we use it in the explanatory data analysis. However, I would like to mention here some point. You need to be careful when you compute the correlation. Let me give you an example. Sometimes you compute variables. I mean, here, for example, the area and the price, they have theoretical reasoning, right? You're going to say the more area, most likely the price is going to increase, right? So there's theoretical reasoning. Sometimes variables might have correlation without any theoretical reasoning. So, for example, if I told you we measure the ice cream sales in a city and the crime rate, and we find them positive, 0.6. What does that mean? Would you say that means the more you sell the ice cream, the more crimes in the city would happen? No, there's no theoretical. Because what does exactly the correlation measure? The correlation measures the movements of two variables over the time. It do not mean the causality. Like in a simple way, if we would like to draw it here, we're going to say, okay, look, here we have over the time the sales of the ice cream. In the winter, we have low sales because it's cold. In the summer, it's increased because it's summer, right? Look into the crime rate. Winter, people staying at home, so we have low crimes. Summer, people travel, go outside, so we have higher crimes. So basically, the correlation look into within time periods. Low, low, high, high. That's mean we have positive correlation. But that does that mean increase in the sales of the crime is the main cause for leading the crime rate? No. That might be another confounding factors. Okay, so this is important. So in this case, when we use the correlation the analysis, you compute first the correlation. You specify there is a correlation between X and Y. Before you use this correlation, you need to look, is there any theoretical reasoning that X will influence Y? Or the area can influence the price? If there is theoretical reasoning, then you can present and use this correlation value. Right. Is that clear? Yeah. Any question? Any question so far? Okay. Okay. One more things here, just as analytics, when you build any model, you need to make sure about different aspects. These include the comprehensibility, justifiability, and operational efficiency. What does that mean in terms of analytics? So comprehensibility, that's mean the model that you build for the stakeholders or that you build to analyze and understand the data are understandable, make sense for them, understandable that they can understand the influence of the parameters. Justifiability, that's mean the parameters or the independent features. For example, you are trying to predict the sales or whatever, using x1, x2, and so on. These x1 and x2 make sense that they are influence the sales. You cannot use parameters that not logically influence the sales and use it in the model. Why is that? Let me just clarify that fastly here. So let's go back to the example where I told you you have, for example, here the ice cream use or the purchase of the ice cream and the crime rate. And you find positive correlation. Basically here, you can build a model, right? And if there is a correlation 0.6, technically, you can predict the crime rate from the number of purchased ice cream. However, this model cannot be justified. Like, I mean, how would the crime rate build the ice cream? And the main issue with this here, because it's not based on theoretical reasoning, so this relation might just occur within this specific time, suddenly, but might be valid in the future. So if I would like to build this model and use it in the future, the behavior might change. In this case, the equation that I developed here might not be valid. So make sure in the models as well that you build for the team, for example, based on the data team project, that you have a good theoretical reasoning, like why I'm including these parameters in predicting the outcome. There is theoretical reasoning that these parameters influence the output. Okay, is that clear? Okay, operational efficiency, that's mean the models are efficient in terms of the operations, in terms of the cost efficiency mainly, or the solution that they propose. Okay, great. The last descriptive analytics that I would like to cover is basically the clustering. So what's the clustering in a simple way? What do you mean by clustering? Or let me give you another way, another example. Imagine that, for example, you have data, whatever, about your clients, your customers, like many variables, like the age of the client, the income level, the purchasing behavior, what product he purchased, and so on. And you would like to understand this data. You have two ways. Either you're going to go and analyze all these variables at higher dimension. So what if the age was young and the income was high, what he would likely to purchase? So you can conduct that manually, and you have unlimited cases, right? That's going to take from you a significant amount of time. One of the approaches that can help us to make the descriptive analytics fast is the clustering. Clustering, in another way, what we're going to do is we're going to provide our data to the model, and we are aiming to find homogeneous clusters. That means clusters with homogeneous, or clusters with homogeneous characteristics within the cluster, but maximize the differences with other clusters. That means basically we're trying, given our data set, it means simply using our data set, multiple different data sets can be at higher dimensions. So you will be trying to find clusters where you maximize the similarity within the cluster and maximize the dissimilarity within other clusters. So let me give you an example of this. I mean, simple clustering example at a one dimension. If you have the sales or the income level, low income level, like $5,000 per year, $10,000 per year. moderate income level, 50, 60, $70,000 per year, and extremely high income level, like 300,000 per year, 400,000 per year. So these are naturally three different clusters where it usually is high income, medium income, low income. This is at one dimension. At three dimensions, similar to the example that I provided at the beginning of the class, where we have information about the income level of the customers, the distance that they are traveled to purchase, and the price that they are paying for a specific product. The income, the distance traveled, and the price they are paying. So here, common clusters find that, for example, extremely wealthy individuals with high income, we found that the distance they travel is low distance. They don't go for like to shopping in extremely like far distances, but the price they are paying for is a little bit higher. So this is one homogeneous cluster. So here I reveal the characteristics as a descriptive analytics for the data using the clustering. Another cluster we find that medium income, we find that the range of travel can be longer, but the amount they are paying is lower. So this is another homogeneous cluster. Is that clear? Yeah. So that's basically in a simple way how we can use the clustering for conducting descriptive analytics. I'm just gonna go fastly through the clusters, just to get an idea about the clusters if you didn't use it before. So clustering can be hierarchical or non-hierarchical approaches. The difference between them, hierarchical, it has logical classifications, like for example, animal species. So here you can classify them into different species, but you can collect them to a bigger species, for example. Non-hierarchical here, like no unrelated data. You cannot relate it together. And mainly, how does the clusters work? So here an example of hierarchical, where, like for example, all the animals like belong to one category, then this can be classified into two categories and so on, which is, I think I presented in a slide here. Here, for example, all the animals, then owls or the eagles, and then the parrots, and then chicken, ducks. Well, I mean, to subcluster. So this kind of a clustering, we call it hierarchical cluster, because they have common characteristics within specific groups. Generally, the clusters are basically based on finding distance. So we would like to have common groups such that we maximize the distance between the groups. And the distance can be computed using different ways, either Manhattan distance, Euclidean distance. Different ways for computing these distances. Euclidean distance is the square root of the distances. The Manhattan distance is just the value of the distance in x and y as an absolute value. Which is, again, some algorithms, basically most of the clustering algorithms are based on maximizing the distance between different clusters. Some algorithms use Euclidean distance, some algorithms using the Manhattan distance between the clusters. So the Manhattan distance between this cluster in x and y, or the direct Euclidean. I'm trying to reshape these clusters to maximize these distances. The amount of clusters, like clustering to two categories, 3 or 4, is the decision of the analyst, which as well can be calibrated. So basically, this is the clustering. So having two groups and trying to maximize the distance. Distance can be measured in different ways and different approaches, either taking the centroid for this cluster, or taking the average for all the points with respect to all the points, or the average for the farthest point or the closest point. So all the clustering algorithm at the end, they work on the same concept, but they either apply different clustering methods or different ways to calculate these distances. All right, and here we mentioned the hierarchical structure. Right, is that clear? Any question? Any question about the clustering? Any questions so far?